For decades, the search for life followed a strict formula. Find the star, measure the distance, and look for liquid water. If a planet orbits within that specific habitable zone, the surface thaws out and can support an ocean. Earth is the standard model for this rule. To maintain a liquid sea, we rely on the sun to keep the water from freezing solid. Because of that reliance on solar warmth, the outer regions of the solar system were largely written off. Out past the asteroid belt, scientists assumed any water would be permanently locked up as frozen rock. But exploration of these distant moons has revealed an entirely different mechanism for sustaining liquid water, suggesting that the sun is not the only way to power a liquid world. Take Jupiter's moon Europa, or Saturn's moon Enceladus. On the surface, the temperature drops to -220 degrees Celsius. It is a punishing, lethal cold. Yet, underneath those miles of rock-hard crust, both of these moons hide vast global oceans of liquid saltwater. To maintain a global sea in the deep vacuum of space, far beyond the reach of solar heat, something else has to be generating immense quantities of energy. The heat source is found in the gravitational influence of the host planets. Jupiter and Saturn exert a constant pull on their orbiting moons. These moons fly in elliptical orbits. Nearing the gas giant, gravity pulls harder, stretching the moon. Moving away, it relaxes. This rhythmic kneading generates intense friction. Deep inside, tremendous orbital energy converts directly into heat. This friction is so intense it heats the moon's rocky silicate interior, turning the core into a powerful thermal engine. Gravity itself replaces the star's radiation, acting as an invisible stove that heats the moon entirely from the inside out. To sustain an ocean, that internal heat has to be contained. On Europa, a crust of ice 15 to 25 kilometers thick acts like the lid of a pressure cooker, trapping the thermal energy and holding the pressure needed to keep the water liquid. This thermal model shows a struggle between two heat sources. Weak sunlight warms the equatorial surface, while internal tidal heat pushes up from the poles. These competing zones drive deep convection currents. Solid ice deforms, cycling material between the surface and the ocean. Because this crust is constantly churning and reforming over the liquid below, impact craters are quickly erased. This is why Europa remains the smoothest object we have ever observed in the solar system. While Europa keeps its ocean tightly sealed, Saturn's moon Enceladus has a much thinner crust at its south pole, riddled with deep fractures. Through these cracks, Enceladus is actively venting. Internal pressure forces towering plumes of water vapor and ice grains directly out into the vacuum of space. By spraying its ocean into orbit, Enceladus provides a rare opportunity to sample the water without drilling through miles of solid ice. NASA flew the Cassini spacecraft through one of those plumes to capture and analyze the raw chemical makeup of the water vapor. The data revealed oxygen and nitrogen-bearing organic compounds, the precursors to amino acids, along with distinct traces of molecular hydrogen. These elements are the specific chemical signatures created when scalding water violently reacts with silicate rock. These findings point to a deep sea floor where active hydrothermal vents are spewing minerals directly into the water. A continuous supply of heat, liquid water, and minerals leached from a rocky core creates the chemical soup necessary to support biological life. At the bottom of Earth's deepest trenches, miles away from the reach of the sun, entire ecosystems thrive around these identical vents. These organisms survive through chemosynthesis. Rather than using solar light, they extract their energy from the chemical reactions driven by the Earth's internal heat. If even a single microbe survives the same way inside these icy moons, it suggests that the recipe for biological development is a universal constant, not an anomaly localized to Earth. The upcoming Europa Clipper mission is designed to verify this. It will scan the moon's ice shell to map out the specific chemistry occurring at the boundary between the ocean and the crust. We are exploring a universe where biology does not require the warmth of a star. It only requires the interaction of gravity, rock, and water, and vastly expanding the frontier of astrobiology.